In this video, you'll find the equation of continuity of fluid. So first of all, consider a continuous motion of fluid like this. Now draw an imaginary surface in the motion, that is like this, and the surface is S, that is a closed surface. Now V is the volume bounded by this surface. Okay, so the amount of mass flowing into this surface through the boundary per unit time is given by minus surface integral of rho v dot ds. Here v is the velocity of the fluid, and now if psi be the amount of mass created per unit volume per unit time, then the increase in mass in the volume is given by volume integral of psi dv. Hence, increase in mass within the volume in unit time is given by del T of volume integral of rho dv. Okay. Now from the conservation of mass, we can say that this quantity plus this quantity is equal to this quantity. So minus surface integral of rho v dot ds plus volume integral of psi dv, that's equals to del T of volume integral of rho dv. Okay. Now we apply the divergence theorem in that case, and the divergence theorem is like this: surface integral of A dot ds is equal to volume integral of divergence of A dv. So applying this formula in that case, we get that's equals to minus divergence of rho v into dv. Sorry, there will be no vector. Okay, plus volume integral of psi dv equals to del T of volume integral of rho dv. Okay. Now taking this volume integral common, we get divergence of rho v plus psi equals to triple integral of del rho del t dv. Okay. Now removing the integral from both sides, we get that is minus divergence of rho v plus psi, that's equals to del rho del t. Okay, and from this del rho del t plus psi, plus divergence of rho v equals to psi. Okay, and this equation is called the continuity equation of fluid. Now if there is no source or no sink in the closed surface, then we can say that psi, that is equals to 0, and from this we can say that del rho del t plus divergence of rho v equals to 0. That is another form of continuity equation. Okay.